The last part of Focus 3 of quantum quarks is cloud chambers. We're going to use secondary sources to learn about how we can see radiation in cloud chambers as specified in the syllabus. So what is a cloud chamber? A cloud chamber is a device that lets us see radiation because radiation is not normally visible unless you use some sort of detector. Now, people who work in radiation industries or industries associated with radiation often wear badges, radiation badges, or they can use Geiger counters, and they'll just detect radiation. But other things like cloud chambers, bubble chambers, and modern radiation detectors cannot just detect radiation, but actually show the path of the radiation as well. So a cloud chamber is probably something you should know. It's a device in which alcohol vapor condenses along the path of radiation, allowing the radiation trail to be seen. Now, what does it consist of? Well, there's a little schematic of a cloud chamber. It basically consists of a few things. First of all, it's got to be a radiation source. The radiation source usually sits inside the chamber somewhere, so you insert a radioisotope inside the chamber to produce the radiation that's to be observed. What else do you need? You need some sort of light source. The light source is there to illuminate the trail, so it lets you see the trail. Without the light source, you can't see the trail, which makes the whole thing a bit pointless. The next thing, though, is the chamber. The chamber is very important. At the top of the chamber, you've usually got some reservoir, or say something like filter paper, which has been soaked with alcohol, and that alcohol evaporates into vapor. At the bottom of the chamber, you've got dry ice. So that keeps it very, very, very cold at the bottom. And what that happens is it means you've got a temperature gradient inside the chamber from very cold to warm at the top. And what that means is any of the alcohol vapor which evaporates, and alcohol does evaporate quite readily in warm temperatures, as it evaporates, it gets supercooled as it passes down through the chamber. And what supercooled is, it means it's cooled to below its melting point, and therefore that vapor really wants to condense into droplets. But it hasn't condensed right now, so it's supercooled. It's vapor that should be condensed into liquid. And the last thing sometimes people mention in a cloud chamber is an electric field. Some people say you need a very strong electric field across the chamber before you start, and the whole point of that is to make a very strong electric field in the chamber, which should remove any stray ions in the chamber before you start the experiment. Although that's not mentioned in all sources. The main things I think are the light source, the radiation source, and the chamber having a temperature gradient and alcohol inside. So how do the trails form? Well, as the radiation from the radiation source passes through the chamber, it collides with an ionizers, and for those who don't do chemistry, ionizers just means to remove electrons from. It ionizes air molecules along the path, and this produces a trail of ions or charged particles along the path of the radiation. There's a little diagram here which I think is in your notes. So what we've got here is these are just the air particles floating around inside the chamber. You've got the radiation travelling through the chamber like this, going this way, and every time it bumps into a particle, it produces an ion. So it's producing a trail of ions along the path of the radiation. Now, we said before the alcohol vapor was supercooled inside the chamber. That supercooled vapor wants to condense, and that vapor will readily condense on these into liquid droplets on these ions. And these droplets then reflect the light. There should be a little P there, not droplets. And these droplets reflect the light from the light source. Dear me. And this can be seen as a vapor trail on the path of radiation. So what happens is these ions are very good sites for the vapor to condense, and so everywhere there was an ion along the path, these little liquid droplets start forming on those ions. So everywhere the radiation's been, it leaves a trail of ions. Everywhere there's ions, you'll get droplets, and those droplets can now reflect the light that's coming in from the light source, and you can see the light reflecting off those droplets, which is like a little trail or a vapor trail where the radiation went. Okay, now alpha particles. Alpha particles have high ionizing power. That means they readily collide with molecules and produce a lot of ions along their path. But that also means their penetration distance isn't very far because they lose a lot of their energy very quickly as they collide with an ionized molecules. This means that alpha particles give short and wide trails, but their trails are usually straight, as their relatively large mass means they're not deflected very far off their path. So a typical alpha trail looks something like this. This is looking down inside a cloud chamber. You've got your alpha source in the middle here, and these are the thick, short alpha trails in little straight lines coming out from that alpha source. So alpha trails, very important, you know, they've got short, wide, distinct trails. Beta particles, though, have moderate ionizing powers. They don't ionize as strongly as alpha. Thus, their trails are thin, they don't produce as many ions, but they're longer because they can penetrate further, they don't lose as much energy as quickly. But however, their low mass means that if you've got very slow-moving beta particles, they can be deflected off their path. They can be bounced around when they collide into ions, so sometimes you get bent paths for low-speed beta particles. So this diagram here shows you the thin trails of beta emissions. Here you've got some very high-energy electrons. Okay, they're travelling in straight lines, very thin trails, and here you might have a low-speed beta particle that's being bumped around as it produces its ions on the trail. Normally for gamma Gamma is so low ionizing, you rarely see a trail from gamma because it will pass straight through the chamber without causing any ion trails. There might be a few little droplets formed, but not enough so you can actually see a trail from the gamma. What this is here, here's a picture from a cloud chamber. See if you can spot a beta trail and an alpha trail inside this chamber. Here you go, some thinking music. Let's see if you got it right. There's an alpha trail, nice short and wide alpha trail, and a long thin beta trail running along here. So there you go, alpha and beta trails. This next one is a picture from a cloud chamber. There's a video linked inside your document. I might also send you an email with a link to it as well. It's quite a good video showing a cloud chamber. This is a picture of something inside a cloud chamber. See if you can figure out what it is. So what are the trails first, and what could this possibly be caused by? Well, what it is actually similar to what we call tracing. Now, these are actually alpha trails. They're short and fat. These little things, they're all lots of little alpha trails. And what's actually happened here is they've puffed a radon gas inside the chamber. Now, radon is a radioactive gas, and it travels through the chamber, emitting, decaying very quickly into alpha particles. So what happened is, as the radiation source was released, as it's spreading out, wherever the gas front is, you can see radiation. In a few seconds' time, that be a bit further along. Before this, it would have been much closer in again. So over time, as that gas spreads out through the chamber, you can see where the gas is by where the radiation is coming from. And this is very important when we go to study radioisotopes in terms of tracing. What you do, if you're trying to observe the passage of something through something where you can't see it, you put a radioisotope inside. So if you, for example, added a radioisotope to fluid as it's passing through a pipe, by detecting where the radiation is, you can see where the fluid is in the pipe at the same time. Or if you want to see the flow of a chemical through a human body, you can add some radioisotopes to that chemical, put it inside the person's body, and then using some sort of radiation camera, see where the radiation is, so you know where that chemical is inside the body, and that's called tracing. They also do it with plants too, to see uptake of fertilizers in plants. And my pen's going a bit crazy here, sorry with those strange trails appearing everywhere. Okay, but even though we've just been studying cloud chambers, this is now going a bit beyond what you need to know for Focus 3. Modern detectors don't use cloud chambers anymore. They use pretty high-tech semiconductor devices to measure radiation sources, and here is an example of a detector you might see in something like a particle accelerator, and it's got a series of different chambers detecting different sorts of radiation. And as you can see here, each layer detects a different sort of radiation. And this is the sort of detector they use in the Large Hadron Collider in Switzerland, the one that discovered the Higgs boson. There'll be some pictures soon. They don't just detect which radiations were there. They often put big magnetic fields around it as well, so the particles will deflect in magnetic fields. So therefore, by measuring the curvature, they can figure out what sort of charge and size and speed these particles have as well. The events are actually quite complex. They have to use a lot of computer power to actually figure out what particles are going where. Here is two schematics of what sort of particles come out of a particle collision. This was in very high energy experiments. We've got one particle traveling very fast this way, one particle traveling very fast this way. They collide in the detector, and when they collide, their combined energy gets turned into mass. A whole lot of new particles are created, and those particles fly out from the collision site and are affected by the magnetic fields. They curl around, and the big machine, that big detector, detects all these different sorts of radiation. This is a picture of one of the events that discovered the Higgs boson. These things marked in red, they're the distinguishing radiation lines. These are the distinct radiation lines that were predicted from a collision that produced Higgs bosons. That's one of the bits of evidence that was used for a Higgs boson discovery. Here's a picture of the Atlas detector, the big detector at CERN, the one that actually picked up the Higgs boson radiations. And as you can see, it's a big chamber, as we said before, but it's absolutely massive. There's a person to scale, and there's a person actually standing next to the detector. And these are all the many detecting devices around this detector to try and pick up all that radiation that's coming out of these collisions. It's quite mind-blowing. This is just some pictures of where they were actually making it. Just the complexity of the circuitry and the computing hardware involved, all the wires involved, and actually plugging this thing together. Just the amazing complex circuitry just blows me away how this thing was put together. It just really is quite an amazing feat of engineering. Now, this isn't a cloud chamber at all. This is something we talked about previously. This is a neutrino detector. This is a mountain in Japan, as you can see here, and this tiny little dot in the middle is this chamber here. This is the ginormous chamber used to detect neutrinos. This whole chamber is usually filled with very pure water, and as the bazillions and trillions of neutrinos pass through this every second, every now and then one of them collides with that pure water in just the right way to produce a photon, and that photon actually leaves the collision event actually traveling faster than the speed of light normally travels in water. And just like when an aeroplane travels faster than the speed of sound in air, it produces a sonic boom, that produces like the sonic boom equivalent of light and produces what we call Chekhov or Chenkov radiation, and that radiation is then detected by these things here. Now we learn about photomultipliers in ideas implementation. They're very, very sensitive detectors of just 1 or 2 photons of light, and they can be used to detect these neutrino events. And this is just one example. There's a whole of these around the world, but it's pretty amazing the actual size of these things and the complexity. And these are these very delicate photomultiplier tubes. Wouldn't want to necessarily have this person's job trying to fix them. Here's a little information about that detector. It's called the Super K. It's in Japan. This came from Wikipedia. If you want to look it up, you can. There's some information just there.